Hello everyone, it's great to be here at the Monster Scale Summit and share a story about optimizing deduplication in recommendation systems when we reduce cost by 90%. Let me introduce myself. I'm Andrei Manakov. I have more than 13 years experience in industry, including many fields, desktop, mobile and web development. For the last 10 years, my core interest is distributed systems. Currently, I'm working in ScyllaDB developing machine learning infrastructure. In free time, I like writing posts about distributed systems and databases. Here is my plan for this talk. I want to start with quick intro into our products and scale we operate at. Then I want to explain what is the duplication problem and why is it important. Then I want to explain initial state of the system. And then most of the time I will cover all optimization which have been done, and it will be tiny conclusion by the end. Let's get started. Firstly, ScyllaDB is the largest social media platform in India with more than 180 million monthly active users and 2.5 billion interactions per month, like shares, comments, and etc. Moj is a short video applications like TikTok. It has more than 160 million monthly active users and more than 6 billion video plays per day. The core of both of these products is a smart feed empowered by personalized recommendations. And the main goal for every recommendation system is deliver the most relevant content per users. Yes, and duplications play a vital role in achieving this by removing already seen content from the candidates. Without deduplications, users will see repetitive content all the time. So, deduplication is a typical part of typical flow in recommendation systems. When firstly we fetch candidates from usually from some vector databases, then we filter some candidates based on various criteria, including the deduplications. Then we score and rank remaining candidates using machine learning models, then sort them by the score and return top of them to the users. During last year, we managed to reduce cost by 90%, and as well, we were able to reduce latency from 50 milliseconds to 8 milliseconds. Let me briefly explain our initial state. And there are the most important concepts in duplications. Viewed post. It's a content which have been viewed by the user. We can define it more strictly like last m post viewed by the user in the last n days. And send post. Send post are content which have been sent to the users, but we don't know about anything about any interactions with them. We can define it strictly like last m post sent to the user during last n hours. Why do we need both of them? I guess it's not quite obvious. Let me explain. Viewed posts are tracked on the user devices. Then periodically they are sent to our backends. They go through the several queues and then saved to a database. So there is a delay between actual event and the time when we save it to database. And it can happen it's possible that we will send duplications in repetitive, in sequential feed requests. To address these problems, we have send post, which is saved in our database just before sending candidates back to the client. So we won't have any duplications because of using send post for duplications. But why do we need viewed post in this case, right? It's a fair question. In feed response, we send multiple posts at the same time, but there is no guarantee that user actually will see all of them. And if we rely only on send post, we will deduplicate relevant but not seen content all the time, which might impact negatively to feed quality. I think it's clear for now. Let's go to the architecture details. Initially, we developed the systems heavily reliant on the Google Cloud technologies. So we had basically view events. View events are sent to Google Pops-up queue. Then we have a Dataflow job, which aggregates events from a Pops-up queue. per users over some period of time and write a batch of the post to one cell to a big table. We have a send post. Send posts are saved to a Redis queue just before being sent to the client application, and a queue implemented with a linked list. Also, we have the deduplication service, which combine send post and feed service and view post all together and send it to the feed service. Deduplication service is written by Golang and is hosted in a Kubernetes cluster. Okay, let's go to the optimizations. Firstly, we reviewed all technology we have used and decided to choose more efficient ones. We replaced Google PubSub with Redpanda. Redpanda is a Kafka killer, basically written in C++. It's more efficient. Also, we replaced Google Bigtable with ScyllaDB, and we replaced Google Dataflow with Apache Flink. Overall, this change helped us to reduce cost to 60% of initial cost. Originally, I wanted to use not percentage but actual dollars, but unfortunately, I'm not allowed to do that. So sorry for that. I will keep in talking about percentage of initial cost. In next two slides, I want to explain a bit deeper about databases and streaming jobs. As I said, originally we used for streaming, for aggregation events, we used Dataflow jobs. It's a fully managed solution, and it has simplified API, so it's really great technology, especially for prototyping, and you're able to deploy a job without writing a single line of code. Unfortunately, on heavy load, it gets pretty costly. So we decided to choose more advanced technology like Apache Flink. It's a self-hosted solution, so we have to have own cluster and maintain it by ourselves. But it worth it because actual job cost has been reduced by 93%. So it's quite impressive actually. Databases. Both Google Bigtable and ScyllaDB have own advantages and some similarities. First of all, both databases are optimized for heavy write workload. Also, we are able to use quite similar schema. Basically, we have a partitioning by user ID, and we store all posts in one column, as a string in this case. In our products, load it's changed significantly during the day, and at night our load in more than 10 times less than during a peak time in the evening. So afterscaling will be very helpful in this case, and Google Bigtable supports afterscaling. So ScyllaDB unfortunately doesn't support afterscaling, and we have to provision clusters according to a peak time, and even having some buffer in case any load spike. A brand new tablets significantly improve elasticity of the database, but anyway, it doesn't solve the problem fully. In addition, Google Bigtable have advanced garbage collection rules, and it's possible to keep and limit row numbers per partitions, basically, and it's possible to have time to live for a cell. ScyllaDB supports only time to live. And with ScyllaDB, actually, it's possible to face a large partition problem if you have much more rows or events per one user. Actually, yes. On the other hand, ScyllaDB is built using a third-party architecture, and it's extremely optimized database. So it has better performance, it has lower latency than Bigtable, it's proven. And it turned out that over-provisioned ScyllaDB cluster significantly cheaper than Bigtable clusters with afterscaling, which again quite impressive to be honest. And also ScyllaDB supports workload prioritizations, and it's quite a unique feature, I believe, because it's help to do resource-based isolations between different workloads. And in our case, it's quite critical because our read path is critical because it directly impacts to the user experience, and we can sacrifice any latency spikes or any availability. but we have basically accept higher latency during writes, or maybe even lost some writes. Another big step for us was optimizing resource allocations. Well, it seems obvious, it's not so straightforward. So, we focus mainly on 3 key areas. We started with optimizing Kubernetes resource. We change Kubernetes pod autoscalers and increase target CPU utilizations, which actually lead to more CPU utilization per pod. Unfortunately, it uncover all inefficiency in your applications, because it will be more garbage collection pressure, you will see more muted contentions, and you need to fix it and configure different runtime parameters and fix all remaining problems. Next area was Apache Flink autoscaler. It was again not so straightforward. Apache Flink autoscaler, let me explain it. Basically, Apache Flink job has own execution pipeline, which contains multiple tasks. Apache Flink autoscaler monitor busy metrics in these tasks and analyze it. Busy metrics efficiently means amount of milliseconds in seconds when the task actually is executed. And it can change the level of parallelism for the tasks and generate some scaling events. Scaling events would mean that job will be recreated with new level of parallelism. And efficiently, it will stop all event processing. And if you have large execution pipeline with many tasks, it will lead to a lot of scaling events, and job will never be stable after that. So it actually even forced us to fork autoscaler for some systems. Fortunately enough, for deduplication pipeline, it was quite smooth. And ScyllaDB resizing. As I said before, we used over-provisioned ScyllaDB cluster originally. And after some monitoring, we realized that we can do scale even more. At first glance, and ScyllaDB is built to utilize all available resources and prioritize critical tasks over non-critical ones. So we can easily see CPU utilization up to 100% without any system degradations. And we realize that we are able to reduce cluster size even more without any latency degradations. I don't have enough time to explain it in details. You can use this QR code and find blog post with details. After all the steps, we managed to reduce cost to 45% of the initial cost. Next optimization was not so fancy actually. As I do believe that every system is supposed to have a clear problem statement, well-defined product metrics, and quite useful and obvious use cases. But in real life, I believe it never happens, and every software engineer seeing code some unclear places, some not obvious use cases, and some parameters without explanations why actually we use one value but not another. And I do believe that we don't that we should question any unclear code, any use case, if you want to have cost-efficient and performance systems. And we did it. Actually, I don't want to explain all use cases we have, every use cases we fixed, but I want to show only one example which doesn't require any context. So we have a let's see, we have a ScyllaDB schema here. In the row we store a list of the posts. Also we have a partition key by user ID. We have classical key by the time, right? So and we have during fetching all rows by the user, we use some limit m, and also we have time to live n, basically n days. So in practice, m and n, it's a limit in our sliding windows where we do deduplications. But how to choose the proper values? So answer is pretty simple. We need to launch a A/B test. So we split all users by the groups and use different parameters for every groups, and we checked basically compare final metrics for between these groups. And it turned out that we used to have two large windows actually, and reducing these windows we were able to even improve user metrics as well as we reduce disk size and reduce latency a lot. Overall, we launched more than 10 different A/B tests, and we reduced the latency from 40 milliseconds to 8 milliseconds. As I said, we reduced database size, and also we were able to reduce load to the systems. Overall cost has been reduced to 30% of initial cost. Next step was storage size optimizing. Firstly, I want to explain why it's really important for ScyllaDB. ScyllaDB read performance depends on the cache, actually. Cache allocates all available space, and less data size, more rows fit in the cache. More rows in the cache, better cache hit rate. Better cache hit rate, we have less disk reads. And less disk reads, we also have less CPU utilizations. So, optimizing storage size, we improve CPU utilizations as well as disk size, which I believe quite obvious. And in practice, we store in a rows list of the post IDs, and they're actually numbers. So we want to compress sequential numbers in this case. We consider three options here. First one is a Bloom filter, which is in practice probabilistic specification hash set, right? It offers pretty nice compressions, but it's probabilistic, so it leads to some false positive result. It's obvious we can have a trade-off between space and false positives, but anyway, better to have no trade-offs. And false positive in our case would lead to more duplicates in the feed. Right. And also it's impossible to restore post ID after you insert it to a Bloom filter, which is not a huge problem, but anyway, it's not really good thing for us. Next one was roaming bitmaps. It's bitmaps optimized for stored integer, but unfortunately it showed us pretty bad result. Only for huge number of integers we got a good compressions pressure. And next solution, which we actually choose, was a delta-based compressions. So we decided to use the moment that we have actual sequential numbers. So we decided to store only delta between them. It's algorithm explanations. So basically we have array of numbers, then we sort the array, then we basically calculate deltas between neighbors, and then we encode it using protocol buffers. Protocol buffers for integers saves only meaningful bits. So it doesn't store all int 64 integer. As a result, we were able to reduce storage by 60%, as well as reduce CPU usage by 25%. And as a result, overall cost has been dropped to 20% of the initial cost, which is quite impressive as well. Next optimization was about send post, was around send posts. But first, let me remind you state of the systems. We have a viewed post, which are stored in ScyllaDB. We have a send post, which are stored in ReSys. After compression optimizations and after resizing, ScyllaDB resizing, we realize that ScyllaDB is cheaper in ReSys in respect to gigabytes. And as viewed post and send post basically are same, so they have just different limits, we managed to move send post to ScyllaDB. So our cost has been reduced as well to 17%, not a bit budget, but fortunately it improved maintainability of the system because we don't need to maintain two databases anymore. And this is last step of our cost optimization journey, is the cloud-specific cost reduction. It's actually a wide topic, but I want to highlight just key moments here. First, the computation part. Every cloud provider have different provision models for virtual machines. And it's important to understand and choose the proper provision model for you. In general, there are two different provision models. One provision model is on demand. When you get a virtual machine, you can use it as long as you want. Another provision model is on spot nodes. In this case, there is no guarantee at all. If you get a virtual machines, it can be evicted anytime. And so for stateless application, it will be best if we use, obviously, on spot nodes and on demand nodes as a backup. And fortunately, CastAI and some of the other products support to help us to configure Kubernetes pool in such way. So it reduced actually cost for the system a lot, as well as for whole organization actually everywhere. And another point is traffic. We optimize traffic between different zones. But question was, what is a zone, right? Efficiently, zone is a different data centers. And every cloud provider have multiple data centers in one region. In case you want to support high availability for your product, you can't deploy everything only to one data center. So you have to spread across multiple, because one data center can be down due to some catastrophic event, for example. It's not really common. It's not really common to have it happens, but anyway. And many cloud providers actually charge you for the traffic between different data centers. It's not avoidable to completely. It's not this traffic not avoidable for databases for queues. You can just compress data, maybe use some different retention policies in order to reduce it. But anyway, you will have it. But you can completely eliminate it in several use cases. For example, for Redpanda or Kafka consumer, you can configure follow fetching feature. In this case, consumer will connect to a broker in the same zone. So as a result, you won't have any inter-zone traffic between the consumer and the queue. For ScyllaDB, you can configure token-aware policy and recovery policy in your driver. In this case, the application will connect a coordinator in the same zone. And as you use token-aware policy, the coordinator actually will have data. So it will be less traffic inside the cluster. The next one is the Kubernetes. Right, so we hosted our microservice in Kubernetes. And in order to reduce inter-zone traffic between microservices, it's quite simple to configure topology-aware routing for your ingress. However, it uses best effort approach. Anyway, you'll have something about 5 or 10 or maybe even 15% of inter-zone traffic. So in order to completely eliminate it, you can choose another service mesh solutions. And in our company, we finally decided to build own service mesh solution based on Envoy proxy. As a result, we don't have any more inter-zone traffic between microservices. So it was the last step, and finally we have reduced cost to 10% of the initial cost. We still have, to be honest, multiple ideas how to even optimize it more, but it's not really reasonable in current state. So thank you all for listening. In case if you have any question, please feel free to ask me in the chat, and or contact me later on by email or in Twitter. Thank you. Bye.